When wind-driven rain is slamming into the side of a building at 60 miles an hour, the structural envelope faces a severe environmental threat. Water under pressure will find its way through almost any microscopic flaw. Against that threat, modern architecture employs open-joint wood cladding, presenting a minimalistic aesthetic with clean vertical lines. But looking closely at the surface, you will notice intentional gaps running the entire length of the vertical wood boards. This presents an intuitive paradox. Why would high-performance construction intentionally leave gaps that allow water and wind past the exterior skin? In this engineering approach, the exterior wood functions as a sacrificial screen rather than a primary weather seal. This strategy relies on decoupling the aesthetic layer from the building's structural core, allowing environmental forces to be managed before they ever reach the interior envelope. For decades, construction relied on the traditional barrier wall paradigm. The strategy was straightforward: attempt to perfectly and completely seal the outermost layer of a building against all moisture. The physics of building materials makes perfection impossible. Temperature swings cause expansion and contraction. Ultraviolet light degrades sealants. Over time, microcracks form, compromising barriers. Once water breaches a sealed system, the wall's primary defense becomes its greatest liability. The trapped moisture cannot evaporate back out, leading to internal rot and eventual structural failure. The structural alternative is the pressure-equalized Rainscreen. Rather than fighting a losing battle against nature, this system expects water penetration and engineers a way to handle it. By introducing a physical gap behind the outer facade, the system breaks capillary action. Water might get past the wood, but without a continuous material path, it cannot be sucked into the inner structural walls. Anticipating water intrusion and managing it through a decoupled screen proves to be a far superior engineering strategy than relying on an impossible permanent seal. This cross-section details the internal anatomy of the wall assembly. On the far left, the interior structural wall serves as the baseline support. Directly attached is the primary thermal defense, a thick layer of mineral wool providing R40 resistance. It is this thick insulation layer, completely hidden from view, that dictates the building's internal climate control, not the wood you see on the outside. Next is the ventilated airspace, a distinct channel designed for fluid dynamics. Finally, suspended outside sits the open-joint cladding, acting purely as an impact shield against driving rain. The building's physical aesthetic has been structurally decoupled from its environmental control layers. Designing intentional gaps in the physical shield introduces a new vulnerability. Standard construction materials degrade rapidly when exposed to direct, prolonged sunlight. To protect the insulation behind those gaps, engineers use a highly specialized barrier. This thin layer is a UV-stable membrane wrapped completely around the insulation block. Standard house wraps would turn brittle and flake away under the daily bombardment of ultraviolet light through the open joints. This specialized membrane acts as the assembly's true, durable weatherline. This introduces a mechanical problem. You need to mount heavy exterior wood shielding over a physical air gap and through thick insulation, without creating metal thermal bridges that leak heat directly into the structure. To maintain the R40 integrity, the facade is secured using thermally broken cladding clips. This inset shows how the hardware supports the extreme weight of the wood while interrupting the conductive heat transfer path. The durability of the entire wall relies directly on this invisible, highly specialized material science operating quietly behind the wood. With the static structure established, we can examine the dynamic fluid physics occurring continuously within that ventilated airspace. This diagram reveals the solar chimney effect. The dark cladding is a passive solar collector. Sunlight hits the wood, transferring heat into the cavity. Sensor data shows ambient temperature at 21 degrees, but the cavity spikes to 32. The thermodynamics are immediate. That 11-degree temperature differential causes the air within the cavity to expand, decreasing its density. This heated, buoyant air rapidly rises upward through the gap, seeking the exhaust vent at the parapet. Escaping air creates a vacuum at the base, continuously pulling fresh ambient air through the bottom intake vent. This self-sustaining, continuous fluid motion, driven purely by temperature differentials, is the solar chimney effect. By utilizing the air gap, this facade weaponizes solar heat to power its own continuous, mechanical-free ventilation system. Maintaining this constant convective loop provides aggressive moisture management for the building. Any wind-driven rain that manages to pass through the open joints, or any internal condensation that forms on the materials, is immediately subjected to the continuous upward draft. The moisture is evaporated and purged before it can penetrate the membrane. The second major structural benefit is thermal buffering against extreme summer heat. As the external wood bakes in the sun, the drafting air inside the chimney physically strips the radiant heat gain away. It carries the hot air up and out of the building before that heat can conduct through the mineral wool and into the living space. This bar chart compares the resulting mechanical cooling loads. A sealed dark facade absorbs and transfers heat inside, driving up air conditioning demands. The ventilated Rainscreen physically exhausts that heat, significantly lowering the load. The solar chimney actively protects both the moisture integrity of the structural frame and the long-term energy efficiency of the interior climate. Looking back at the completed exterior, the physical gaps between the wood boards take on a completely different context. The industry is moving away from passive barriers that inevitably trap moisture, favoring screened walls that expect the elements and systematically manage them. The most advanced building science no longer tries to stubbornly fight natural elements with perfect seals. Instead of resisting, this active system takes the relentless energy of the sun and puts it to work. True high-performance architecture engineers pathways for nature's forces, like solar radiation and convection, to ease a heavy lifting of protecting the structural envelope.